Section 10 of the ABC of Relativity by Bertrand Russell. This LibriVox recording is in the public domain. Chapter 10. Mass, Momentum, Energy, and Action. The pursuit of quantitative precision is as arduous as it is important. Physical measurements are made with extraordinary exactitude. If they were made less carefully, such minute discrepancies as form the experimental data for the theory of relativity could never be revealed. Mathematical physics, before the coming of relativity, used a set of conceptions which were supposed to be as precise as physical measurements, but it has turned out that they were logically defective, and that this defectiveness showed itself in very small deviations from expectations based upon calculation. In this chapter, I want to show how the fundamental ideas of pre-relativity physics are affected, and what modifications they have had to undergo. We have already had occasion to speak of mass. For purposes of daily life, mass is much the same as weight. The usual measures of weight, ounces, grams, etc., are really measures of mass. But as soon as we begin to make accurate measurements, we are compelled to distinguish between mass and weight. Two different methods of weighing are in common use, one that of scales, the other that of the spring balance. When you go on a journey and your luggage is weighed, it is not put on scales but on a spring. The weight depresses the spring a certain amount, and the result is indicated by a needle on a dial. The same principle is used in automatic machines for finding your weight. The spring balance shows weight, but scales show mass. So long as you stay in one part of the world, the difference does not matter. But if you test two weighing machines of different kinds in a number of different places, you will find, if they are accurate, that their results do not always agree. Scales will give the same result anywhere, but a spring balance will not. That is to say, if you have a lump of lead weighing 10 pounds by the scales, it will also weigh 10 pounds by scales in any other part of the world. But if it weighs 10 pounds by a spring balance in London, it will weigh more at the North Pole, less at the equator, less high up in an airplane, and less at the bottom of a coal mine, if it is weighed in all those places on the same spring balance. The fact is that the two instruments measure quite different quantities. The scales measure what may be called, apart from refinements which will concern us presently, quantity of matter. There is the same quantity of matter in a pound of feathers as in a pound of lead. Standard weights, which are really standard masses, will measure the amount of mass in any substance put into the opposite scales. But weight is a property due to the Earth's gravitation. It is the amount of force by which the Earth attracts a body. This force varies from place to place. In the first place, anywhere outside the Earth the attraction varies inversely as the square of the distance from the center of the Earth. It is therefore less at great heights. In the second place, when you go down a coal mine, part of the Earth is above you, and attracts matter upwards instead of downwards, so that the net attraction downwards is less than on the surface of the Earth. In the third place, owing to the rotation of the Earth, there is what is called a centrifugal force, which acts against gravitation. This is greatest at the equator, because there the rotation of the Earth involves the fastest motion. At the poles it does not exist, because they are on the axis of rotation. For all these reasons, the force from which a given body is attracted to the Earth is measurably different at different places. It is this force that is measured by a spring balance. That is why a spring balance gives different results in different places. In the case of scales, the standard weights are altered just as much as the body to be weighed, so that the result is the same everywhere. But the result is the mass, not the weight. A standard weight has the same mass everywhere, but not the same weight. It is in fact a unit of mass, not of weight. For theoretical purposes, mass, which is almost invariable for a given body, is much more important than weight, which varies according to circumstances. Mass may be regarded, to begin with, as quantity of matter. We shall see that this view is not strictly correct, but it will serve as a starting point for subsequent refinements. For theoretical purposes, a mass is defined as being determined by the amount of force required to produce a given acceleration. The more massive a body is, the greater will be the force required to alter its velocity by a given amount in a given time. It takes a more powerful engine to make a long train attain a speed of 10 miles an hour at the end of the first half minute than it does to make a short train do so. Or we may have circumstances where the force is the same for a number of different bodies. In that case, if we can measure the accelerations produced in them, we can tell the ratios of their masses. The greater the mass, the smaller the acceleration. We may take, in illustration of this method, an example which is important in connection with relativity. Radioactive bodies emit beta particles, electrons, with enormous velocities. We can observe their path by making them travel through water vapor and form a cloud as they go. We can, at the same time, subject them to known electric and magnetic forces, and observe how much they are bent out of a straight line by these forces. This makes it possible to compare their masses. It is found that the faster they travel, the greater is their mass, as measured by the stationary observer. The increase is greatest as applied to their mass as measured by the effect of a force in the line of motion. In regard to forces at right angles to the line of motion, there is a change of mass with velocity in the same proportion as the changes of length and time. It is known otherwise that, apart from effective motion, all electrons have the same mass. All this was known before the theory of relativity was invented, but it showed that the traditional conception of mass had not quite the definiteness that had been ascribed to it. Mass used to be regarded as quantity of matter, and supposed to be quite invariable. Now mass was found to be relative to the observer, like length and time, and to be altered by motion in exactly the same proportion. However, this could be remedied. We could take the proper mass. The mass is measured by an observer who shares the motion of the body. This was easily inferred from the measured mass by taking the same proportion as in the case of lengths and times. But there is a more curious fact, and that is, that after we have made this correction, we have still not obtained a quantity which is at all times exactly the same for the same body. When a body absorbs energy, for example by growing hotter, its proper mass increases slightly. The increase is very slight, since it is measured by dividing the increase of energy by the square of the velocity of light. On the other hand, when a body parts with energy, it loses mass. The most notable case of this is that 4 hydrogen atoms can come together to make one helium atom, but a helium atom has rather less than 4 times the mass of one hydrogen atom. We thus have 2 kinds of mass, neither which quite fulfills the old ideal. The mass as measured by an observer who is in motion relative to the body in question is a relative quantity, and has no physical significance as a property of the body. The proper mass is a genuine property of the body, not dependent upon the observer, but it also is not strictly constant. As we shall see shortly, the notion of mass becomes absorbed into the notion of energy. It represents, so to speak, the energy which the body expends internally as opposed to that which it displays to the outer world. Conservation of mass, conservation of momentum, and conservation of energy were the great principles of classical mechanics. Let us next consider conservation of momentum. The momentum of a body in a given direction is its velocity in that direction multiplied by its mass. Thus, a heavy body moving slowly may have the same momentum as a light body moving fast. When a number of bodies interact in any way, for instance by collisions or by mutual gravitation, so long as no outside influences come in, the total momentum of all the bodies in any direction remains unchanged. This law remains true in the theory of relativity. For different observers, the mass will be different, but so will the velocity. These 2 differences neutralize each other, and it turns out that the principle still remains true. The momentum of a body is different in different directions. The ordinary way of measuring it is to take the velocity in a given direction, as measured by the observer, and multiply it by the mass, as measured by the observer. Now the velocity in a given direction is the distance traveled in that direction in unit time. Suppose we take instead the distance traveled in that direction while the body moves through unit interval. In ordinary cases this is only a very slight change, because for velocities considerably less than that of light, interval is very nearly equal to lapse of time. And suppose that instead of the mass as measured by the observer we take the proper mass. These two changes increase the velocity and diminish the mass, both in the same proportion. Thus the momentum remains the same, but the quantities that vary according to the observer have been replaced by quantities which are fixed independently of the observer, with the exception of the distance traveled by the body in the given direction. When we substitute space-time for time, we find that the measured mass, as opposed to the proper mass, is a quantity of the same kind as the momentum in a given direction. It might be called the momentum in the time direction. The measured mass is obtained by multiplying the invariant mass by the time traversed in traveling through unit interval. The momentum is obtained by multiplying the same invariant mass by the distance traversed in the given direction in traveling through unit interval. From the space-time point of view, these naturally belong together. Although the measured mass of a body depends upon the way the observer is moving relatively to the body, it is nonetheless a very important quantity. For any given observer, the measured mass of the whole physical universe is constant. The proper mass of all the bodies in the world is not necessarily the same at one time as at another, so that in this respect the measured mass has an advantage. The conservation of measured mass is the same thing as the conservation of energy. This may seem surprising, since at first sight mass and energy are very different things. But it has turned out that energy is the same thing as measured mass. To explain how this comes about is not easy. Nevertheless, we will make the attempt. In popular talk, mass and energy do not mean at all the same thing. We associate mass with the idea of a fat man in a chair, very slow to move, while energy suggests a thin person full of hustle and pep. Popular talk associates mass and inertia, but its view of inertia is one-sided. It includes slowness in beginning to move, but not slowness in stopping, which is equally involved. All these terms have technical meanings in physics, which are only more or less analogous to the meanings of the terms in popular talk. For the present, we are concerned with the technical meaning of energy. Throughout the latter half of the 19th century, a great deal was made of the conservation of energy, or the persistence of force, as Herbert Spencer preferred to call it. This principle was not easy to state in a simple way because of the different forms of energy. But the essential point was that energy is never created or destroyed, though it can be transformed from one kind into another. The principle acquired its position through Joule's discovery of the mechanical equivalent of heat, which showed that there was a constant proportion between the work required to produce a given amount of heat and the work required to raise a given weight through a given height. In fact, the same sort of work could be utilized for either purpose according to the mechanism. When heat was found to consist in motion of molecules, it was seen to be natural that it should be analogous to other forms of energy. Broadly speaking, by the help of a certain amount of theory, all forms of energy were reduced to two, which were called, respectively, kinetic and potential. These were defined as follows. The kinetic energy of a particle is half the mass multiplied by the square of the velocity. The kinetic energy of a number of particles is the sum of the kinetic energies of the separate particles. The potential energy is more difficult to define. It represents any state of strain which can only be preserved by the application of force. To take the easiest case, if a weight is lifted to a height and kept suspended, it has potential energy, because if left to itself it will fall. Its potential energy is equal to the kinetic energy which it would acquire in falling through the same distance through which it was lifted. Similarly, when a comet goes round the sun in a very eccentric orbit, it moves much faster when it is near the sun than when it is far from it, so that its kinetic energy is much greater when it is near the sun. On the other hand, its potential energy is greatest when it is farthest from the sun, because it is then like the stone which has been lifted to a height. The sum of the kinetic and potential energies of the comet is constant, unless it suffers collision or loses matter by forming a tail. We can determine accurately the change of potential energy in passing from one position to another, but the total amount of it is to a certain extent arbitrary, since we can fix the zero level where we like. For example, the potential energy of our stone may be taken to be the kinetic energy it would acquire in falling to the surface of the earth, or what it would acquire in falling down a well to the center of the earth, or any assigned lesser distance. It does not matter which we take, so long as we stick to our decision. We are concerned with a profit and loss account, which is unaffected by the amount of the assets with which we start. Both the kinetic and the potential energies of a given set of bodies will be different for different observers. In classical dynamics, the kinetic energy differed according to the state of motion of the observer, but only by a constant amount. The potential energy did not differ at all. Consequently, for each observer, the total energy was constant, assuming always that the observers concerned were moving in straight lines with uniform velocities, or, if not, were able to refer their motions to bodies which were so moving. But in relativity dynamics, the matter becomes more complicated. We cannot profitably adapt the idea of potential energy to the theory of relativity, and therefore the conservation of energy, in a strict sense, cannot be maintained. But we obtain a property closely analogous to conservation, which applies to kinetic energy alone. As Eddington puts it, the kinetic energy is not always strictly conserved, and the classical theory therefore introduces a supplementary quantity, the potential energy, so that the sum of the two is strictly conserved. The relativity treatment, on the other hand, discovers another formula, analogous to the one expressing conservation, which holds always for the kinetic energy. The relativity treatment adheres to the physical quantity and modifies the law. The classical treatment adheres to the law and modifies the physical quantity. The new formula, he continues, may be spoken of as the law of conservation of energy and momentum, because, though it is not formally a law of conservation, it expresses exactly the phenomena which classical mechanics attributes to conservation. It is only in this modified and less rigorous sense that the conservation of energy remains true. What is meant by conservation in practice is not exactly what it means in theory. In theory, we say that a quantity is conserved when the amount of it in the world is the same at any one time as at any other. But in practice, we cannot survey the whole world, so we have to mean something more manageable. We mean that, taking any given region, if the amount of the quantity in the region has changed, it is because some of the quantity has passed through the boundary of the region. If there were no births and deaths, population would be conserved. In that case, the population of a country could only change by emigration or immigration, that is to say, by passing across the boundaries. We might be unable to take an accurate census of China or Central Africa, and therefore we might not be able to ascertain the total population of the world. But we should be justified in assuming it to be constant, if, wherever statistics were possible, the population never changed except through people crossing the frontiers. In fact, of course, population is not conserved. A physiologist of my acquaintance once put 4 mice into a thermos. Some hours later, when he went to take them out, there were 11 of them. But mass is not subject to these fluctuations. The mass of the 11 mice at the end of the time was no greater than the mass of the 4 at the beginning. This brings us back to the problem, for the sake of which we have been discussing energy. We stated that in relativity theory, measured mass and energy are regarded as the same thing, and we undertook to explain why. It is now time to embark upon this explanation. But here, as at the end of chapter 6, the totally unmathematical reader will do well to skip, and begin again at the following paragraph. Let us take the velocity of light as the unit of velocity. This is always convenient in relativity theory. Let m be the proper mass of a particle, v its velocity relative to the observer. Then its measured mass will be m divided by the square root of the quantity 1 minus v squared, while its kinetic energy, according to the usual formula, will be 1/2 mv squared. As we saw before, energy only occurs in a profit and loss account, so that we can add any constant quantity to it that we like. We may therefore take the energy to be m plus 1/2 mv squared. Now, if v is a small fraction of the velocity of light, m plus 1/2 mv squared is almost exactly equal to m divided by the square root of the quantity 1 minus v squared. Consequently, for velocities such as large bodies have, the energy and the measured mass turn out to be indistinguishable within the limits of accuracy attainable. In fact, it is better to alter our definition of energy and take it to be m divided by the square root of the quantity 1 minus v squared, because this is the quantity for which the law analogous to conservation holds. And when the velocity is very great, it gives a better measure of energy than the traditional formula. The traditional formula must therefore be regarded as an approximation, of which the new formula gives the exact version. In this way, energy and measured mass become identified. I now come to the notion of action, which is less familiar to the general public than energy, but has become more important in relativity physics, as well as in the theory of quanta. The quantum is a small amount of action. The word action is used to denote energy multiplied by time. That is to say, if there is 1 unit of energy in a system, it will exert 1 unit of action in a second, 100 units of action in 100 seconds, and so on. A system which has 100 units of energy will exert 100 units of action in a second, and 10,000 in 100 seconds, and so on. Action is thus, in a loose sense, a measure of how much has been accomplished. It is increased both by displaying more energy and by working for a longer time. Since energy is the same thing as measured mass, we may also take action to be measured mass multiplied by time. In classical mechanics, the density of matter in any region is the mass divided by the volume. That is to say, if you know the density in a small region, you discover the total amount of matter by multiplying the density by the volume of the small region. In relativity mechanics, we always want to substitute space-time for space. Therefore, a region must no longer be taken to be merely a volume, but a volume lasting for a time. A small region will be a small volume lasting for a small time. It follows that given the density, a small region in the new sense contains not a small mass merely, but a small mass multiplied by a small time, that is to say, a small amount of action. This explains why it is to be expected that action will prove of fundamental importance in relativity mechanics. And so, in fact, it is. All the laws of dynamics have been put together into one principle, called the principle of least action. This states that in passing from one state to another, a body chooses a route involving less action than any slightly different route. Again, a law of cosmic laziness. The principle is subject to certain limitations, which have been pointed out by Eddington, but it remains one of the most comprehensive ways of stating the purely formal part of mechanics. The fact that the quantum is a unit of action seems to show that action is also fundamental in the empirical structure of the world. But at present there is no bridge connecting the quantum with the theory of relativity. End of section 10.